This video is for the second part of CED 2.6, so I'll call it part 2. And if you watched the earlier one, you were learning the different new rules that we could apply to the power rule. And this second video now is a little more involved, and I'm going to use our new rules to solve interesting problems such as finding where horizontal tangent lines are, working with normal lines, making piecewise functions differentiable, some somewhat gnarly applications, and worthy of its own video. Okay, two kind of fun problems on this page. The first one is a horizontal tangent line problem. And the question asks, when does a function have a horizontal tangent line? Well, so if we were looking, say, at something like that, we have a horizontal tangent line when the slope of that tangent line is 0. So to find where a function has a horizontal tangent line, we set the derivative equal to 0, and that's how we do it. So here is our function. So first we're going to find the derivative using the power rule. We're going to then set that equal to 0, solve for x, and it's when x is equal to negative 7/8. A normal line. A normal line goes through the same point as the tangent line does, but it is perpendicular to the tangent line at that point. So remember, when something is perpendicular, its slope is going to be the opposite reciprocal. So if it was 2/3, it'd be negative 3/2, etc. So in this problem, they ask us to find an equation of the normal line of f of x at x equals 3. So first of all, what we have to do is we have to find the point. So it's going to be the same point that you would have for your tangent line. So 3f of 3, we find f of 3 by just plugging it into this equation. So that's going to be 27 minus 4 times 9, 36, plus 3 plus 3, that's negative 3. So my point is going to be at 3, negative 3. Here's where it is. And that's what the tangent line would look like. Now, because we want the normal line, it's going to go through that same point, but it's going to be perpendicular. That is a little skewed looking, but anyway. Okay, so we need to find the slope of the tangent line. So the slope of the tangent line is just f prime of 3. So f prime of x, I'm going to just use f again, is 3x squared minus 8x plus 1. F prime of 3 is 3 times 9, which is 27, minus 8 times 3, which is 24, plus 1, so that's 4. Therefore, my perpendicular slope is going to be the opposite reciprocal. So I'm going to use the same point, but my new slope is negative 1/4. So it's going to be y plus 3 equals negative 1/4 x minus 3, because we're using this point. There you have it. Now we're going to work to find if piecewise functions are differentiable at some given value of x. And you recall from our last unit, 2.5 I think, we were using the alternate formula with limits f of x minus f of a, etc., and setting the right and left hand limits equal to each other. Well, with our shortcuts, we can just find the derivatives of each piece of the piecewise function and then plug the number c in and hope that we get things that are equal, and that's the equivalent of using that limits action. So let's do this first one. So first we have to determine whether or not the piecewise function is continuous. So we're going to come over here and we're going to go, is it continuous at x equals -1? So the first thing that we do is we figure out what f of -1 is. We're going to use that lower function. So it's -7 times -1, which is +7, minus 3, which is 4. That also happens to be the limit as x approaches -1 from the right of f of x. And what's the limit as x approaches -1 from the left of f of x? Well, let's see. So that would be 5 times 1, which is 5, minus 3, plus 2. So that also is 4. Those two are equal. They're equal to, so the limit is 4. F of -1 is 4. So yes, it's continuous. So now, here comes a new part. Is it differentiable? Since we've established that it's continuous. So first you're going to find f prime of each subfunction. So 5x squared goes to 10x plus 3. And that's when x is less than -1. And -7x minus 3 goes to just plain old -7. And that's when x is greater than or equal to -1. Now we're going to plug -1 into each subfunction. So the first one becomes -10 plus 3, which is -7. The second one's just a constant. It's -7. These things are equal. So the answer is yes, it's differentiable. Now this next problem involves a system of equations. And I'm going to run out of room. So I pasted this onto a new page. And here you go. So they're asking us what values of a and b would make the function differentiable. So generally on these things, you're going to end up with a system of equations. You can see that we have two variables, a and b. Not variables, they're constants, a and b, but we have to figure out what those letters are, what they stand for. And so if it's differentiable, we have to first test if it's continuous. And this is going to give us our first equation for our system. So I'm going to go number 1. F of 3 will exist, okay? And so if I plug 3 in, I'm going to use that x plus b, so I get 3 plus b. My second step is the limits. The limit as x goes to 3 from the right-hand side of this function is 3 plus b, which we just established. The limit as x goes to 3 of this function from the left-hand side, we're going to use the top function, so that's going to be 3 times 3, which is 9, minus 3a plus 2, so that's going to be 11 minus 3a, and these two things have to be equal. So 3 plus b equals 11 minus 3a. And I'm just going to clean this up a little bit, bring my a's over here, 3a plus b, bring my constant 3 over to the other side. And that right there is giving me my first equation, because that's the same thing as f of 3. Okay, now my second equation is going to come from the differentiability. Blah, blah, blah. I hate spelling that. Okay, so f prime of x is going to equal, so we differentiate the first one, 2x. Now remember, a is some constant, so this just becomes minus a, and the 2 becomes a 0. In the second equation, the x becomes a 1, and the b becomes a 0, because b is a constant, greater than 3. We're going to plug 3 in and set these two things equal to each other. So 6 minus a equals 1. Well, that's nice. This is not an ugly system. So a is equal to 5. Lovely. I can come back over here, plug 5 in for A, and 8 minus 15 is negative 7, and so those are my value. There you go. Second part of 2.6.